So today we're going to talk about my favorite topic, which happens to be bonding and coordination chemistry. This is going into chapter 10. Coordination chemistry. Ooh, bonding. So I said we were going to describe how these systems bond. We looked a little bit in that classroom assignment that we just did about bonding. But this chapter is all about how do these ligands actually interact with the metal center. And the reason it's my favorite favorite chapter is these are interactions I never thought about until like I took a course called Organometallics, and then it just blew my mind completely. So let's talk about some of these interactions and some of these weird types of bonds that we may never have considered in organic chemistry or general chemistry. So the first important point is the d orbitals can act as an electron sink or reservoir. D orbitals can behave as an electron sink or reservoir. And this is why they have weird behavior. Okay, so the first question we're going to ask is, what type of orbital overlap can happen with a d orbital? So what type of orbital overlap can occur with d orbitals? Yep, so can you give me examples?
Sigma.
Okay, so if we have a sigma type interaction, that's overlap in how many regions?
1.
Okay, so let's draw a d orbital. What type of overlap do you want to have? Or what orbital is this d orbital going to interact with?
Oh, just a more like an s orbital.
Yeah, but that's an example of one. You can actually interact with any of them as long as it's right. But let's draw one with an s orbital. So
make it easy.
So there's a sign change halfway through, and then we would have an s orbital like that. So that's an example of an s type overlap with a sigma type overlap with a d orbital. We could have two d orbitals that overlap, that produce a sigma. Could have an overlap with a p orbital also to result in a sigma, right? Everybody feels like they can see that and understand that.
Yeah.
Okay, what other type of overlap can they have?
We have pi overlap.
Okay, pi overlap.
Are we worrying about anti-bonding right now? Or are we just
Not right now.
Okay.
Yeah, we'll get to that in a minute. Right now, we'll just draw all bonding cases. Okay, so we got our d orbital. What do you want to have it overlap with?
Let's do a py orbital.
I liked Tara. Tara was drawing it out. Let's do a py specifically. The y
okay,
direction.
px.
You guys are forcing me to have that z axis. I can't ever admit that.
Didn't even think of that.
So there's overlap in how many regions here?
2.
Yep. Okay. Finally, what's the last type of overlap we can have?
Gamma.
Not gamma.
Delta.
Delta. Yeah.
Lowercase delta. Is this lowercase or uppercase delta? Or is
This
the triangle
one's
just
lowercase.
something just completely different?
Uppercase is that one.
Okay.
Rito.
We'll save that for something else, though, even though we use it 10 million times. How many regions of overlap do we have for a delta?
3.
4.
4. Yup. It stinks. It jumps from 1, 2 to 4. Okay.
Is there one with 3?
There is not. There are 3 center bonds that have 3, but we're not going to talk about those quite yet. Okay. We're going to try to draw these with the d orbitals along the sides, so kind of like my hands interacting with one another right now. We're going to show them kind of like that. So there's sort of that overlap that way. We're going to try to draw it. So we'll show like the front lobes interacting with red. And the back lobes interacting with green. And all it really looks like is I just scribbled all over it. But it's meant to show that type of interaction. Okay, so everybody remember those types of overlap. So depending on the occupation of the d orbitals and the type of ligand that you have, you get different types of interactions. So depending on the occupation of the d orbitals and the ligands frontier orbitals, you get different types of bonds. And there are typically 4 types of interactions. So 4 types of metal ligand interactions. What we're going to do now is we're going to go through each of those interactions, discuss them a bit, and give some examples. Okay?
Okay.
Am I okay to move this up
A little.
Yes.
a little? Okay. Like that?
Yeah, now I'm good.
Okay, the first one we're going to have is sigma donor ligands. And these are the type, oops, I have this really crooked. These are the type of ligands we've talked about most of the time so far. So what happens is electron density is donated from a ligand to a metal. What type of bond do you think?
D to a.
Probably sigma.
Yeah, sigma. Via sigma bond. Maybe we should say interaction. Interaction is probably a better word to use. So could you think of an example of a ligand that you know behaves that way?
Hydrogen.
What was that?
Hydrogen.
Just H. Can you be more specific? What type of hydrogen?
A single hydrogen.
Yep, a single hydrogen. So
You can have, like,
hydride does.
Oh, okay.
Sodium
yeah,
hydride.
I see what you're going for.
Sodium hydride.
Mm-hmm.
Yep. So hydrides will definitely do that. What about other ligands that we've seen a lot of? Any monodentate ones that tend to pop up quite a bit?
Like ammonia to like whatever atom, like a platinum,
Yeah.
because we do a lot of platinum. All right.
We're going to look at ammonia to Cu. So copper. So we got this copper atom sitting here. That's meant to be a d orbital. We look at the HOMO, or the highest occupied molecular orbital of the ammonia. It has some electron density. What's going to happen here?
So wait, the HOMO of the ammonia is going to go to the LUMO of the, wait, yeah, to the LUMO of the,
Well, this guy doesn't technically have a LUMO because it's just an atom by itself.
It
okay.
just has like a lowest
It
energy.
just wants to donate it
Its
to it.
d orbitals aren't completely filled.
Yeah.
More favorable.
Yeah. So this is an empty d orbital, essentially. In this case, I don't know, we'll call it the dx squared y squared. So after this is all said and done, what happens is, actually, we're gonna get rid of that copper. We get a sigma type interaction. So where's electron density going to and from again?
Anything, I guess, from the sigma bond interaction to.
Well, I mean, is the
It's going from the nitrogen to the copper because the
Yeah.
copper doesn't have that electron density.
right. So this is empty.
Going to the d orbital.
Yep. Exactly. Okay, can I
Over a little.
like that?
Right there. Empty. Oh.
Yep, empty d orbital. Okay, so we can have sigma donor ligands. What other type of sigma ligands do you think we can have?
Pi donor,
Yep, we can have pi donor. We'll get to that one in a minute.
sigma acceptor.
Sigma acceptors. So am I okay to move this up?
Yep.
Okay. So we also have sigma acceptor ligands. Okay. So what happens is these ligands, they withdraw electron density from metal and give it to the ligand. So this is typically highly electronegative elements. There are other examples like boron trifluoride. That's meant to be a B. So used to writing beta out, I'll try that again. There we go. Okay, so let's look at this type of interaction. So we got a metal. It's got some electron density. And then we got boron trifluoride. What is the hybridization of the boron in this system?
SP2.
Yep. So that means there's an empty p orbital that's just sitting out in space. Okay, tell me what's going to happen.
The electrons will flow to that empty space.
So electrons flow there. And then we get a sigma bond between those two.
So it's flowing, so typically boron, it has 3 bonds, so it's considered like a saturated atom at that point. So it's going to accept more electron density even in this state as like a ligand?
Yes.
Okay.
Yep. It'll take in more electron density, even though there's that formal charge there. Boron does a lot of weird stuff.
So the metal in that case, would that be considered like shaded? So it would have like the electron density?
Oh, like if it's shaded or not shaded, that's really just keeping track of the sign of the atomic orbital, like what location you're considering. So I'm trying to stay away from the shaded and unshaded thing. You do need to consider that though to determine if it's constructive or destructive overlap and what type of bonding you have.
Well, we are saying that d orbital is filled currently.
Yes. Yep.
Okay.
So filled d orbital. I don't know, this could be the LUMO. It might or it might not be. But we'll say unoccupied. State on ligand. And then it makes a bond that way.
Okay, that makes more sense.
Then Josh, I think you said, can I move this up?
Yep.
Okay. Josh, you said one of the other types of interactions we're going to have, and I said, yeah, we'll talk about that one in a minute.
The
What
pi
was that?
donor?
Yep, we got pi donors. Okay, so in this case, where's electron density going to flow to and from?
From the pi bond to the d, or not g, so like
From the ligands, pi bonds to the d orbitals of the metal.
pi bonds. I guess that's like, is that a good way of saying it?
Yeah,
It's
that's,
not bond yet. It's like it's more of the orbitals, but
it could be the orbitals, it could be the bond. They're actually both that happen
okay.
here.
It just sounds a little.
So donates electron density. Yeah, I know it sounds weird to say bonds, but that does happen too. From ligand to metal. Okay. So here's our metal. And we'll highlight that in green. Okay. And we have a ligand. Try to specify that in green. Okay. And which one's occupied again, or what's going to happen?
The ligand, it's is occupied.
Yeah. And so electron density goes from the ligand to the metal, right? And even though I drew 2 electrons kind of down in that lobe of the p orbital, they exist in both of the lobes, right?
Mm-hmm.
Okay. So this is a pi type interaction. Okay, what other type? So what about this d orbital? Occupied, unoccupied?
Unoccupied.
Unoccupied, yeah.
So unoccupied d orbital, and then this is some occupied state. Okay, last type of interaction.
Would it be pi acceptor?
Yep. Pi acceptor ligands. So tell me what's going to happen there.
It's going to go from the metal to the ligand.
Yep. Ligand receives electron density. From metal. So we got our metal. That's a terrible d orbital. I'm ashamed. It's occupied. We have an unoccupied ligand. And just like Tara said, it flows the opposite way. This is still a pi type interaction. Okay. What about the metal and what about the ligand orbitals?
It's a or it's an occupied d orbital and an unoccupied state for the ligand.
Okay. Now, you guys have actually already looked at these types of interactions. Did you ever discuss it this way when you talked about activating and deactivating groups in organic chemistry?
There are so we talked about those when it came to like aromatic chemistry, and we would look at like phenol rings and which groups were activators and deactivators.
Right, but you probably never described it this way. And something that always bugged me is why do the halogens, like, why do they go?
Deactive. Okay.
Yeah. What were you gonna say, Josh?
They were considered like an exceptional like deactivator, while all the other deactivators just weren't like you.
Right, and then as you go down the periodic table, they actually become more activating. That's because they're sigma withdrawing, pi donating. It has to deal all with those types of concepts. So you can actually have two of these types of bonds happening at once. And a great example of this is the ligand carbon monoxide. So ligands can be a combination of these things.
Wait, shouldn't there be one more acceptor donor one?
We got pi or sigma donor, sigma acceptor, pi donor, pi acceptor.
Yeah, what about the other one?
Oh, deltas? We're not going to worry about deltas. There is that stuff, but they don't have much of an influence, and we'll see why. So ligands can be a combination. Oh, actually can have a combination of these interactions. Example, carbon monoxide. So carbon monoxide is sigma donating, but pi accepting. And this is sometimes called back bonding. So it's pretty cool. It's like a yin and yang. There's some give and there's some take. So you have a metal that has a sigma type interaction with the HOMO of carbon monoxide. This d orbital, would you expect it to be filled or empty?
Empty.
Yep. And can you tell me what's going to happen?
Those electrons are going to go to that metal.
Yep. And what type of interaction is that going to be?
Sigma.
Yep. It's a sigma type interaction. So electron density flows from the ligand to the metal. Now we also have another situation.
And this is like at the same time.
Mm-hmm. In this case, I am going to draw the phases of the orbitals. And then we have the pi, one of the pi star orbitals. Oh, actually, I should have been a little more formal. Color that in. All right, then we got pi star. So this is an empty CO orbital, which is the LUMO of this system. And this is an occupied d orbital. So what's going to happen in this case?
It's going to pi accept, so that means from the metal, it's going to be in phase and it's going to pi bond, I guess.
Yep. So electron density is donated from the metal to the carbon monoxide. And this is why carbon monoxide has a really strong bond. So if you notice, so hemoglobin, hemoglobin binds oxygen, right? And it goes through this sort of type of interaction. But carbon monoxide actually kills you by binding really strongly to that iron center. And the way it bonds is through these types of interactions. That's why it's so hard to dislodge carbon monoxide. Okay, so how do we actually know this? We can measure this experimentally. So, question, how do we know CO is a pi acceptor? So if you were going to do some sort of experiment, what would you do?
Have it bond to something and then heat it up and see if it comes off or not.
Okay, yep, so you could do
test
that.
ionization energy, but couldn't you also test like its polarizability and see like where like the electron density on?
Okay, so let's say we wanted to test polarizability or, you know, bond strength. How would you do that in the lab?
Instrumentally, you could use a what is it called?
I think you're just trying to get towards that. This is all computational.
Nope, that's not
Oh,
computational.
okay.
Yep, no, I want to know
can't
like
think
an
of
actual experiment you could do to show that the bonds are changing.
I'm trying to think of the instrument name. What could you use?
So you guys think, let's write down some complexes. So you can synthesize all of these guys. Some of them are extremely poisonous, but you can at least synthesize them.
Oh, can you push it up a little bit? We can't. See.
Okay, so let's say we have all those synthesized. What experiment would you do?
Just to look at the bonding between them.
Mhm.
Just,
To try and quantify the bonding between them.
you could do. What could you do? I'm waking up. Let's think.
So let's name the different types of experimentate or instruments that we have up in the lab and say, would that work or would that not work?
Okay, so UV vis wouldn't work because we're not looking at concentration. We're not really looking at, that doesn't really look at ionization.
Right. So
FTIR
Yeah.
doesn't really.
FTIR, what about FTIR?
I
I didn't
don't
say that. I
think.
said GCMS.
GCMS. So GCMS would give us the identities of all of these. They can tell us a bit about the fragmentation, but they won't be able to tell us about the bonds.
FTIR would
strengths.
let us look at, I guess, that means it would have to be IR reactive.
Yep. So we could use IR to look at like that vibration. Okay. What else?
Could you do? I mean, you could look at the shielding around the carbon if you wanted to do NMR.
You could, but the risky part with NMR with these
Metal.
strands, some of them might be paramagnetic, so you're gonna
Yeah,
run.
that's true.
The one I was looking for was actually IR.
Oh.
So IR spectroscopy. Which is nice because most labs have an IR spectrometer. They're relatively cheap compared to the rest of them. So next, we're going to keep track of the frequency of that CO stretch. The reason it's nice, why is it nice to keep track of that CO stretch?
Well, it's going to change if it's next to different transition metals.
Yep. So it's going to change a lot. And then what's the other benefit of keeping track of a CO stretch?
It'll always be there.
Yeah, it'll always be there. It's really, really sharp. It's easy to tell exactly where it is. So if you look, and if you consider, if you look on the periodic table and you look at these complexes, what do you notice about them? How many electrons are around each of these d orbitals?
So like titanium's gonna be 2.
Yep, 2, but it's got a 2- charge.
So it'd be times 4.
4, yep. Vanadium,
That's gonna
typically.
be 5 then. Right,
Vanadium,
no,
typically
4. That's once again 4. My bad.
4. Chromium,
So 4 automatically.
manganese 2, 1 plus.
4.
4, and iron 4. So they're all the same amount of electrons, but the degree in which they're held changes. So which of these is going to do the worst job of holding on to its electron density?
The titanium.
Yep. Now, the CO stretch, is that getting stronger or weaker?
Getting weaker.
Yes. So, shows weaker.
Okay.
CO bond. Why does that make sense?
Because if it's so the density is moving,
Mhm.
then the density of the that's actually keeping them together is also going to have to change.
Yep, so there will be some from the sigma, but like let's look back
It's a
at
weaker
this.
CO bond because it's more likely to give off the density. It's not as tightly bound to the metal center.
Yep, I forgot to color this in, by the way.
Hmm.
What type of orbital are we donating into?
An empty pi.
Yep, it's specifically a pi star, a pi antibond
Yeah.
orbital, right? So what's going to happen to the bonds between the carbon and the oxygen if we're donating into an antibonding?
Probably get bigger or longer.
Yep, they're going to get longer. That interaction is going to get weaker. And then because of that, that vibrational frequency is going to become less. So shows a weaker CO bond. It makes sense because we're donating into a CO antibonding state. So that weakens that bond. Okay. Okay, so now let's ask the question. I'm going to move this up, but you'll want to look at this while we do that. Question: which metal has the most amount of pi back bonding? And which has the least? Okay, so we're trying to gauge which one has the most, which one has the least. Looking at that table.
Let's see. Titanium then?
So titanium has the most or the least?
Most. Yeah, it has the most.
Yep. Titanium 2 minus has the most. Which one has the least then?
The
Iron.
Yep, and what's the oxidation state on that iron?
2+.
Yep. Because remember, these vibrational frequencies, like we learned in PChem, the greater the oscillation, or the greater the amount of energy to cause that vibration, the more energy you have to put in, right? Which means a stronger bond. Okay? Everyone feel comfortable with that? All right. So I'm going to move this up, and we're going to make another table.
Can I ask a question?
Yeah, sure. What's up?
Can you have sigma back bonding or is it only pi back bonding?
You can have, so you can have sigma donation.
Okay.
You might, most of the time it's just called sigma donation. It's usually not called sigma back bonding,
Okay.
but you could. Okay, so now what we're going to do, we're going to make a table. We're going to list the type of ligands. We're going to have ligand, the type that we have. We're going to have strong pi acceptors. We're going to have weak pi bonding. And we're going to have strong pi donor. Okay, we got lone electron pair donors. We got pi bonding electron pair donors. And we got sigma bonding electron pair donors. Even though this thing won't focus, come on, there we go. Kind of move out a little bit more. There we go. Okay. You guys already know one lone pair donor that's a really strong pi acceptor. What ligand is that?
Carbon monoxide.
Yep. So carbon monoxides. CF3 is an example. Or CR2 plus. Name another ligand.
Amine group.
Yep, the amines. So they're lone pair donors, but they're really weak pi bonding. They don't like to do that. So amines, methyls, hydrides, phenylphosphines. And then some really strong pi donors are CR2 minus, OR minus, and fluorine. Ethylene can form a pi bond, but it does some weak type of pi bonding. Aldehydes also do a kind of weak job. So fluorinated ethylene is actually going to be a really strong pi acceptor because of how it withdraws electron density from that pi bond. O2. And then we got some silanes. And some alkanes. Okay. So having an idea of what is a strong pi acceptor, what's a strong pi donor, and if something can or cannot actually really make a pi bond can help you out in understanding what type of interactions are happening inside of the molecule. Am I all right to move this up? Okay, so now we're going to consider a kind of strange system. The question: how is molecular hydrogen H2 bound in the following complex? We got CR,
So there's only strong pi donors for lone E pair donors.
Can you repeat that, Josh?
So there's only strong pi donors for just for the lone electron pair donors. You're not going to see a lot of those others for, I guess, any of the other two situations.
So yeah, pi bonding electron pair donors. Yeah, you don't see a ton of strong pi donors.
Okay.
You can have some, but generally not too many. Okay, so the next question. We have this complex. How is that H2 bonding in this system? Anybody have an idea?
Well, the way that you have it drawn makes it look like it's both atoms are bonded to the chromium. So
Yeah.
It's like the sigma bond that is what really connects. It's like the molecular orbital that is what bonds the chromium.
That's what we want to do. We want to look at the molecular orbitals of H2. So let's consider MOs of H2. We got electron or energy. H2, like that, right? What's the label of this orbital?
Sigma.
Yep.
Right.
Sigma, and then this guy.
The sigma store.
Yep. Okay, what do those orbitals look like?
Your regular sigma is just going to be like almost a ball.
So you have a bonding interaction between them. Once they overlap, like that, right? What about the anti-bonding?
There's not going to be any overlap, so they get pushed away from each other.
Oops, I colored them in wrong. This one should be empty. Like that. Okay, now let's consider how they'll interact. So now what I'm going to do, we're going to draw those types of interactions, and then we're going to determine if they're, what type of interaction it is. Okay, so this guy, what orbital is that for H2?
Sigma.
Yep, so it's occupied. Sigma, what do you think about this metal d orbital?
Unoccupied.
Yep. Empty metal d orbital. Okay, what's going to happen?
The electrons are going to want to move there.
So electron density moves from where to where?
From the sigma bond or sigma orbital to the d orbital.
Yep. And what type of interaction is that?
I think it's just a sigma interaction.
Yep. Okay. Can you think about an interaction that this anti-bonding orbital could have?
I think that's pi.
Okay. So a pi type interaction? This is where I'd have you come up and draw it on the board. Okay. Now for this interaction to be favorable, how should I fill in the d orbital?
Shaded at the bottom right.
And then up here, right?
Yep.
Okay. So what type of interaction is this?
Pi.
Yep. And which way is electron density going?
From the d orbital to the anti-bonding, because that anti-bonding pair is empty, shouldn't it?
Yep. So if you look at the MO diagram, there's no electron density there in that anti-bonding state. So it has to go from the metal to the ligand. Okay. So what could you say about this is the LUMO, right? LUMO of H2. What about this metal orbital?
Probably homo.
Well, remember, it's an atom.
Oh,
So occupied or unoccupied?
must be occupied.
Yep. And it's metal d orbital. Okay, so that's what's going on here. So am I okay to move this up? Okay, so now let's say, how would we provide experimental evidence for this? So what would you do to show that this is happening?
I mean, this would react under IR as well.
Okay, so let's use the IR. And what should happen, or what are you going to keep track of in the IR?
This would be the, I guess, doesn't HH peak even exist on IR? I can't say I've ever seen anything like that.
Yeah, I've never looked at molecular hydrogen under the IR.
Yeah, I can't say I have either, so I don't know what range I would expect to find that.
Right, but you could find something, right?
Okay, yeah, it's IR reactive.
So let's say we look at the IR of H2 by itself. What will happen to the wave number of that like HH stretch?
If it's going to an empty d orbital,
So IR
is the wave number going to decrease?
Yep. IR mode should decrease in wave number. Basically because we've added electron density into that anti-bonding state. We have also taken electron density away from a bonding state. Okay? Cool. Any other questions? All right, we have some time. We're going to introduce another type of way to look at these systems and explain like the d orbital occupation. Have you guys ever heard of high spin and low spin complexes? Okay. We're going to talk about how do you assess those, and we have kind of a simplified theory to look at these things. So let's start by talking about crystal field theory. So this is used to explain a bunch of different things that we see. Used to explain spectra, structures, and magnetism. And it answers the questions, how are the d orbitals influenced by the ligands interacting with that metal center? So answers the question of how d orbitals of the transition metal are influenced by the ligand. Okay, the way we do this is we assume the ligands are point charges and that the metal is just bathed in a uniform electric field. So this is assuming ligands are point charges. and the d orbitals are bathed in a uniform electric field. I after E. There we go. We did it.
Isn't it I before E except after C?
Damn it.
Or a neighboring way.
Does this field?
You're just always going to be
Not
wrong
bad.
no matter what you say.
Doesn't look right.
Doesn't look great.
It's
Come
I
on.
before.
It's F, isn't it FIELD?
Yeah.
Yeah, it is.
So you had it right the second time.
Damn. So close. One of these times.
It's okay. We know you're smart.
No, I'm not. That's the,
You didn't
And
get
it's
your
more about-
PhD in
it's
English,
like-
you got it in PChem. And
yeah. Like it's more about like how many times have I done this and I still just can't get it right. That's the part that irritates me. Is like I'm okay with being wrong, but just not wrong over the same exact thing a million times. All right. So question. Let's ask what happens as a point charge there we go. Wasn't sure if you guys missed that song or not.
I do.
All the time.
Someday we're gonna hear it years from now, and we're gonna be thrown back to this.
We have a flashback in like a seizure in the middle of like the
Yeah.
parking lot.
And then
where
we'll
I have
text
it.
the group chat.
Yeah. And then you
You'd be
just
like,
start
"Oh."
deriving stuff as fast as possible.
Oh,
Yeah.
of course.
Looking like Charlie Day from It's Always Sunny, where he's got all the like
Yeah.
the strings all over everything. Yeah. Okay, so you got these negatively charged ligands. They get close to these d orbitals. What's going to happen to them? So negatively charged points getting close to systems that have negatively charged particles in them. What type of in? What'd you say, Tara? I'm sorry, I cut you off. One more time.
Repel each other.
Yeah, they're going to repel each other. Yep, there's a repulsive interaction.
Nice shirt, Josh.
Oh,
Yeah.
yeah.
So let's look at an example of the crystal field. Of iron 3+. So first thing is we have to determine how many d electrons does an iron 3+ have. So to do this, you want to count up the total number of electrons in the valence shell. So if we write out the configuration for iron, what's it going to be?
One S, two.
What is it? S.
Oh, we're going just condense.
Yeah. S4 to 3D, how many?
It's gonna be +3, so it's gonna be like 3.
I don't have a table in front of me. I have no idea.
Okay, 3D6. Good count. Okay, now what about Fe3+?
Same thing except 3D3.
Remember, what
No.
gets ionized first?
Oh, wait, no, it's the s orbital. So
S orbitals go first, so those guys are gone.
it'll be 3d5.
Oh,
Yes.
Oh,
Okay.
I was so confused about the first example, but I didn't realize you were just drawing it for regular ion.
Yep, just a regular ion. Okay, so now what we're going to do, sorry, I'm going to run over a little bit, but I want to finish this. So we got free Fe3+. We're only going to worry about those d orbitals. How many d orbitals do I need to draw?
5.
Yep. 1, 2, 3, 4, 5. And how many electrons are in each of these d orbitals?
1.
Yep. 1, 2, 3, 4, 5. Now, what we're going to do is we're going to apply it an electric field. Oh, I know, IE. There we go. The Fe3+. As we apply that electric field, what's going to happen to the energy of these orbitals?
It'll increase.
1, 2, 3, 4, 5. But they all increase at the same rate and the same amount of energy because we've applied a uniform or a crystal field. Now, we add ligands. And we're going to assume an octahedral pattern. So what's going to happen as those ligands approach different orbitals?
They're going to donate their electron density to the d orbital.
Well, remember, they're just behaving as point charges. We're going to pretend
okay.
that they're not, you're right, but we're going to pretend they're not donating anything right now.
So they're going to repel it, so they're going to push the energy back down?
Some are going to go down, some are going to go up in energy.
Oh, okay.
What happens is you get a splitting.
Is it
These
back down
guys-
to like the 0 point, like lower energy, or is it pushed below that?
I'm sorry, can you repeat that again, Josh?
So when the energy is pushed down, is it pushed back down to like the free at the iron energy level, or is it pushed lower, or is
It completely depends on the type of ligand you have.
Okay.
So this is a degenerate, these orbitals are all degenerate with one another. They are triply degenerate. That's why they get the symbol T2D. These are doubly degenerate. That's why they get the symbol EG. So that comes from point groups, molecular orbitals, and irreducible representations. In terms of the orbitals that get shifted, this is the dxy, dxz, dyz. And these guys, this one's the dz squared, this one is the dx squared minus y squared. And what we say is the difference in energy along here, that's given the symbol delta O, where delta is the change, O stands for octahedral. Okay, and that dictates whether if we fill in electrons all along here or we fill in electrons 1, 2, 3, 4, 5. If delta O is really large, what's going to happen? Or how am I going to fill electrons if delta O is really large?
They're all going to go to the bottom.
Yep. What if delta O is really small?
You can have those transitions where it'll go.
I'm
some
sorry,
at
can
the
you?
top. It'll have those transitions where it can go from top and bottom. The electrons can
Right.
go both.
Yep, some will be in they'll be in all of these orbitals. So next time we're going to talk about what dictates that. Why did I put these ones lower in energy and these ones higher in energy? So we're going to talk about crystal field theory, ligand field theory, and then we're going to go into MO theory of all of this. What's important is to understand what we're doing here. So read up on that section. It's taxing, but it'll help you out a ton. Okay. Are there any questions about the material? No?